Welcome back to the deep dive. So today we're doing something a little different.
Yeah, bit of a change of pace.
We're not looking at a news story, really. We're looking at, well, what feels like a philosophy that's just disguised as a piece of software.
I like it.
I mean, we were looking at a stack of documentation here that is, I'm not kidding, heavy enough to be a blunt weapon.
It's a massive stack. I think we might have set a record for the page count on this one,
We
actually.
really might have. We've got the official documentation for version 3.40. We have the Qgis developer cookbook.
Which sounds a lot more delicious than it is.
It does, but it's full of Python code. We've got technical transcripts on LiDAR processing from Lutra Consulting, and then these incredibly dense training manuals from Boston University.
And you need a stack that big.
Yeah.
You really do. Because we're talking about, an absolute beast in the geospatial world.
We're talking about QGIS.
Yeah.
And I want to start with the thing that it jumps out at me immediately from those Boston University slides.
Yeah.
It's the comparison table. You know the kind. Column A is the thing we're looking at. Column B is the competitor.
Sure, the head-to-head.
And you have this tool, QGIS, which it's used by NASA. It's used by local governments, researchers mapping diseases, and the cost listed in that column is just $0.
$0. 0 cents free.
Then right next to it in the slides, you have the industry standard, right? The proprietary giant, ArcGIS.
A big one.
And the cost is, well, it's a subscription. It can run into the thousands depending on what you need.
Oh, yeah, easily.
And my brain immediately goes to that old saying, you get what you pay for.
Of course.
If I buy a generic drill for $10, it's going to burn out the second I hit concrete. So why is QGIS different? How is free not, inferior in this case?
That is the fundamental question, isn't it? And to answer that, you have to look past the price tag and look at the definition of open source they give in the intro docs.
Okay.
It's really about the difference between a black box and what I've heard called a glass box.
A glass box, I haven't heard that before.
Yeah. So think about it. With proprietary software, the black box, you
Yeah.
put your data in, right?
Right.
Let's say you have a list of pollution readings from sensors all over a city.
Okay.
You press a button that says Analyze Hotspots. The software does its thing, lights blink, and it spits out a map with red zones.
And I don't know how it did that.
You don't know exactly how it decided what a hotspot was.
Yeah.
You have to assume the math is right because, the vendor is this massive, reputable company.
Yeah.
But you can't actually check it.
You're just trusting the brand. You're basically outsourcing the validity of your science to a corporation.
Exactly. And in science, trust me, isn't a valid methodology. It just isn't.
Right.
With QGIS, because it's open source, the code is transparent. It's a glass box. If that hotspot analysis looks a little weird to you or a developer you hire can literally open the hood.
You can look at the code?
You can look at the Python code.
Yep.
You can see the math. You can see if they, divided by X when they should have divided by Y.
So it's really about accountability.
It's about accountability. It's about transparency. It's about extensibility. If the tool doesn't do exactly what you want, you don't have to file a feature request and wait 2 years for the next big release.
You can just build it yourself.
You can build a tool yourself. Or, and this is more likely, because the community is so huge, you find that someone in France or Brazil or Japan has already built it and shared it for free.
Which brings us to the identity of this whole thing. I was digging through the history in the Wikipedia source and the docs. It started way back in 2002.
A long time ago, yeah.
Founded by a guy named Gary Sherman. And for a long time, it was called Quantum GIS.
Quantum GIS.
Yeah.
A classic name.
I have to say, Quantum GIS sounds infinitely cooler. It really does. It sounds like something out of a Marvel movie. I'm uploading the coordinates to the Quantum GIS.
It sounds like you're about to travel through time. It does have a certain sci-fi ring to it, doesn't it?
But then in 2013, with version 2.0, they dropped it. Now it's just QGIS. Why? Why the rebrand? Did they lose the rights to the word quantum? Was there a lawsuit from a physicist or something?
No, nothing that dramatic. It was actually an attempt to be less intimidating and more precise. Quantum makes you think of physics.
Sure.
It implies this level of complexity, maybe subatomic complexity, that just wasn't accurate. It's a geographic information system. The Q originally was a nod to the toolkit it's built on, which is called Qt.
QT.
Qt, yeah. It's a cross-platform application framework. It's the reason QGIS could look and feel the same on Windows, on a Mac, and on Linux.
I see.
But really, the name change was just about streamlining. By 2013, everybody was just calling it 2JS anyway. They just made it official to avoid confusion.
Clean branding. I get it. But let's talk about actually getting this thing onto a computer. Because this is where the free part starts to feel a little bit like some assembly required. The installation guide we have. It's not a simple click here to download button.
Yeah.
There are options. There are different flavors of the software.
Right. You don't just download QGIS. You have to choose your path. You've got the LTR, and you've got the latest release.
And they have names. The source mentions version 3.40 is codenamed Bratislava. The latest release, listed, 3.44, is Solothurn. I feel like I'm choosing a European vacation, not a piece of software.
Yeah, they name their releases after the locations of their developer meetings. It's a really nice community touch. It's a little nod to the people who actually built it.
That's cool.
But for the user, that choice between, say, Bratislava and Solothurn is actually critical. LTR stands for long-term release.
That's the Bratislava one in our docs.
Correct. And if you are doing professional work, I mean, if you're a city planner and you need to print a map for a council meeting on Tuesday, or if you're a student submitting a thesis, you install the LTR.
Why that one specifically?
Because it's frozen in time. No new features are added to it. It only gets bug fixes. It is the rock-solid foundation. It is, boring, but in the best possible way.
So it's the safe bet. It's the Volvo.
It is the Volvo, exactly. The latest release, Solothurn in this case, is for the people who want the new toys.
The early adopters.
Right. Maybe there's a new 3D rendering feature or a new way to handle point clouds that just came out. It's in the latest release.
Yeah.
But because it's new, it hasn't been tested by thousands and thousands of users yet. It might crash if you click a specific sequence of buttons.
And then there's the nightly build.
Oh, the dev build. That is the bleeding edge. That is code that was literally written yesterday.
Wow.
The source mentions they're working on the shift to Qt6 for version 4.0 right now. If you install the nightly, you're seeing the future of the software. But you're also absolutely signing up to be a crash test dummy.
I think I'll stick to the LTR then. But even with that, on Windows, there's this thing called the OSGeo4W network installer. I looked at the screenshot in the docs, and I mean, it looks like a hacking tool from the 90s.
It scares a lot of people off. It really does. It's not the prettiest interface, but it is the power user's secret weapon.
How so?
See, QGIS doesn't live in a vacuum. It relies on a dozen other open source libraries. It uses GDL for reading images. It uses GRASS for topology, PROJ for coordinate systems.
It's like a team of Avengers.
Exactly. QGIS is just the face of the operation as Captain America. The OSGeo4W installer manages all those dependencies, all the other heroes. It allows you to have the LTR and the dev build installed side by side without them fighting over who gets to use the Python library. It keeps your whole sandbox organized.
Okay, so we get it installed, we launch it, and we are staring at a completely blank white screen.
The void.
And the interface is full of buttons, these tiny little icons that look like ladybugs and wrenches and graph paper. This is the now what moment.
This is where most people quit.
But we aren't quitting. The tutorial on importing spreadsheets walks us through a scenario that I think is the perfect hello world for GIS.
I agree.
We have a text file from NOAA. It's a list of significant earthquakes from 1900 to 2000.
A classic data set. Everybody uses that one.
It's a TSV file, tabs separated values. And we want to see these earthquakes on a map. So first step is we open the data source manager.
Which, by the way, is a huge improvement in recent versions. It used to be you had a different button for every single file type. Now it's this unified command center for all your data.
Okay, so we select delimited text, we point it to the file, and the first trap, according to the tutorial, is the delimiter itself.
Yes. This trips people up constantly. If you tell QGIS it's a CSV, a comma-separated file, when it's actually TSV tab separated, the preview window just looks like garbage.
What happened?
It just puts everything in one giant column. It can't parse it. You have to explicitly tell the software, look for tabs between the data, not commas.
But the real trap, the one that I am convinced every single person who has ever used GIS has fallen into, is the X and Y fields.
Oh, the coordinate trap, yes.
You have a column called latitude and a column called longitude. You have a box for X field and a box for Y field. And logic dictates. Well, what does logic dictate? In my head, latitude sounds like ladder, which goes up and down, so...
Well, it's a good association. That's correct.
But I've definitely 100% put latitude and X before, And then my earthquakes that should be in Japan end up somewhere off the coast of Antarctica or rotated 90 degrees and flipped.
It happens to the best of us.
Yeah.
The tutorial offers a mnemonic, but let's just break down why it is the way it is. Think back to high school algebra.
Okay.
The Cartesian plane. The x-axis is the horizontal line, right? The y-axis is the vertical line.
Okay.
Longitude measures how far east or west you are from the prime meridian in London. That is horizontal movement along the map. That is x. A good way to remember is long is along the horizon.
Long is along. Okay, that sticks.
And latitude measures how far north or south you are from the equator. That is vertical movement up and down the map. That is y. So longitude is x, latitude is y.
I feel like I need to write that on a sticky note and put it on my monitor for the rest of my life.
You absolutely should. Because if you get it wrong, QGIS will dutifully plot the points. It doesn't know you made a mistake. It just puts the data where you told it to. And suddenly your whole map is mirror imaged and rotated, and you don't know why.
So we get the X and Y right, we hit add, and suddenly, boom, we have dots on the map. We have what the docs call vector data.
Yes, and this is a really good time to pause and just define our terms, because the sources reference vector and raster constantly.
Right.
What we just created, these discrete points, that's vector data. Vector is anything with a hard edge. A point, a line like a road or a river, or a polygon like a building footprint or a country boundary. It's all just mathematically defined coordinates.
Physically connect the dots.
Exactly. And the other side of that coin is raster data.
Raster is a grid, right? Like a photo.
Think of a digital photo. It's made of pixels. In GIS, a raster is usually a satellite image or an aerial photo. But it can also be data. A digital elevation model, or a DEM, is a raster where every single pixel represents a height value instead of a color.
So vector is like drawing with a pen, and raster is like painting with pixels.
That's a perfect way to put it. And newer versions of QGIS, as we see in the docs, are supporting even more complex types like mesh data and point clouds, which I'm sure we'll get to.
Oh, we will, but for now, we have our earthquake points on the map.
We do.
But here is where the real nightmare begins. The Section 3 nightmare. The Coordinate Reference System, the CRS.
The bane of every GIS analyst's existence. I have seen grown men weep over CRS errors.
The guide has a whole section just titled, "My data set is in the wrong place." It sounds like a cry for help. Why is this so hard? I mean, the Earth is the Earth. Why can't the computer just know where the points are supposed to be?
Because the Earth is not a sphere.
Yeah.
And it is definitely not a flat piece of paper.
It's a lumpy potato. I've heard that one.
It is a lumpy, spinning, slightly squashed potato. And we are trying to represent that 3D potato on a 2D computer screen. To do that, we need a mathematical bridge. And that bridge is the CRS.
And there are two main types, right? GCS and PCS.
Correct. GCS stands for Geographic Coordinate System. This is the raw data. This is the system that models the potato itself.
Well, okay.
It uses angles, degrees, latitude and longitude. WGS84 is the most famous one. It's what your GPS uses. It's just saying you are at this angle from the center of the Earth.
Okay, so that tells me where I am on the globe.
But it's terrible for measuring distance. A degree of longitude at the equator is about 111 kilometers. A degree of longitude near the North Pole is almost 0. The lines converge.
Right.
So if you try to calculate area in degrees, the math gets incredibly complex and is usually wrong.
So you need to flatten it.
You need to project it. You need a PCS, a projected coordinate system. This is the act of taking that 3D surface and smashing it flat onto a plane so you'd measure things in meters or feet.
Like unpeeling an orange and trying to flatten the peel on the table.
Exactly. And what happens when you try to flatten an orange peel?
It tears, it stretches, you can't do it perfectly.
You cannot do it perfectly. This is the fundamental, unbreakable rule of cartography.
Yeah.
You have to sacrifice something. You can preserve area, you can preserve shape, you can preserve distance, or you can preserve direction. But you cannot preserve all of them at once. It's impossible.
This brings up the Mercator defense that's mentioned in the source. Because we all learn in school to hate the Mercator projection. On a wall map, it makes Greenland look the size of Africa. It's a lie.
It is a lie about area. It massively distorts area. But it tells the absolute truth about angles.
Angle.
Mercator is what's called a conformal projection. That means if you draw a 90-degree turn on the map, it represents a true 90-degree turn in the real world. For a ship captain navigating the Atlantic in the 1700s, that was the only thing that mattered.
Oh, I see.
He didn't care how big Greenland looked. He cared that his compass bearing was a straight line on the map.
So that's why Google Maps uses it.
Exactly. Because when you're looking for a coffee shop, you want the street corners to look like square corners. You want the navigation to make sense. So Google uses a version called Web Mercator. It sacrifices global area to preserve local shapes.
But here's where the user gets into trouble. The assign projection versus reproject layer issue. The guide highlights this as a major source of error.
Oh, this is the classic. This gets everyone. Let's say you have a layer that seems to be in the wrong place. Maybe it's floating in the ocean off the coast of Africa.
The Null Island.
The Null Island, yeah. The temptation is to use the tool called assign projection to say, no, QGIS, you're wrong. This is actually California.
That sounds logical. You're correcting it.
No, you are lying to the software. Assign projection only changes the label on the data. It's like taking a thermometer that measures in Fahrenheit and pasting a Celsius sticker over the F.
You haven't changed the temperature.
You haven't changed the temperature. You've just ensured that everyone reading it is going to be completely wrong.
So when would you ever use assign?
Only if the data came with no label at all, and you happen to know for a fact what it's supposed to be. Maybe the person who created just forgot to include the projection file.
Okay, so if my data is in the wrong place, or if I want to change it from lat-long to meters, what do I do?
Use reproject. That is the mathematical engine. It takes every single coordinate pair, runs it through the complex transformation formula, and writes a brand new coordinate pair in the new system. It actually converts the Fahrenheit to Celsius mathematically.
Got it. And QGIS has this on-the-fly feature. The source says it allows you to view different coordinate systems at the same time.
It's a lifesaver, but it can also be a trap. QGIS is very smart. If you load a layer in WGS 84, which is in degrees, and another layer in a UTM zone, which is in meters,
Okay.
QGIS will do the math in the background just in RAM to line them up visually, so they look correct on your screen.
But the underlying data hasn't actually changed.
Exactly. The files on your hard drive are still in different systems. So if you try to run a spatial analysis like select all earthquakes within 100 kilometers of this city, and one layer is in degrees and the other is in meters, the algorithm will freak out.
What happens?
It might return 0 results. Or worse, much worse, it might return a result that is completely wrong but looks plausible.
That's the dangerous one, the plausible wrong answer.
Always.
And then there's one more CRS issue, the datum shift. The guide talks about data being just slightly off, like the road is 10 meters to the left of where it should be on the satellite image.
This is where the lumpy potato comes back to haunt us. A datum is our attempt to model the center and the shape of the Earth.
Okay.
NAD 27, the North American datum of 1927, used a specific estimate of the Earth center based on ground surveys. NAD 83 from 1983 uses a much better one based on satellites. The difference between those two models can be anywhere from 10 to 100 meters on the ground.
So if I mix old data with new data,
You get a ghost image, everything is shifted, the data is not broken, it's just using a different definition of where 0 is. You have to apply a datum transformation to make them line up.
it really is rocket science.
It literally is. It's geodesy. That's the science.
Let's move away from the math headaches to something more fun, the App Store aspect. The plugins.
This is the ecosystem. This is why QGIS wins, in my opinion.
The YouTube transcript we have lists a bunch of must-have plugins,
Ah.
and the first one on the list is Quick Map Services.
Oh, that's essential. That should be built in, honestly. When you first open QGIS, the background is just white. It's a void. You have no context for your data.
Right.
Quick Map Services adds a menu where you can click Google Satellite, OpenStreetMap, Bing Roads, and it just streams that base map directly into your view.
So you instantly know where in the world you are.
Instantly. It grounds your data in reality.
Then there's one called MMQGIS. They call it the Swiss Army knife.
Yeah, that's a good description. It just fills in a lot of the little gaps in the core software, does things like geocoding.
What's that?
Taking a list of street addresses in the spreadsheet and finding their latitude and longitude coordinates using Google or OpenStreetMap APIs.
Oh, that's useful.
Super useful. It creates hub lines, drawing lines from a center point out to many spokes. It's just a big collection of tools that the core developers didn't put in, but that almost everyone needs eventually.
And one that really caught my eye here, QGIS2 Web.
The democratizer.
Because usually if I want to put my map on a website, I need to know JavaScript, right? I need to know a library like Leaflet or OpenLayers. I need to be a coder.
And QGIS2 Web basically says, no, you don't.
Really?
You build your map in QGIS, you style the colors, you set up the pop-up so when you click an earthquake, it shows the magnitude. Then you open this plugin, you click export, and it writes all the code for you.
It literally generates the HTML file and everything.
It generates a whole folder.
Mhm.
Inside is an index.html file, some JavaScript files, a data folder. You double-click that HTML file, and boom, your map is in your browser. Zoomable, clickable, interactive. You can upload that folder to any web server, and you are officially a web mapper. No coding required.
That is incredible.
What?
But what about the hardcore science stuff? There's one here called the Semi-Automatic Classification Plugin, or SCP.
SCP. That is for remote sensing.
Ah.
This is for people who want to look at satellite imagery like from Landsat or Sentinel. And not just look at the pretty picture, but actually analyze the light.
What do you mean analyze the light?
Well, satellites capture light in wavelengths our eyes can't see.
Yeah.
Infrared, near-infrared.
Right.
Vegetation, for example, reflects near-infrared light very, very strongly. Concrete doesn't. So the SCP allows you to teach QGIS. You draw a little box over a forest and say, this is what trees look like. You draw a box over a city block and say, this is what concrete looks like.
And then it learns from that.
It runs an algorithm like minimum distance or maximum likelihood, and it classifies every single pixel in the entire satellite image based on those signatures you gave it.
So it turns a photo into a data map.
It turns a photo into a map of urban versus nature, or healthy forest versus unhealthy forest. You can track deforestation this way. You can track urban sprawl, all from a free plugin in a free piece of software.
That segues perfectly into the cutting-edge section of our outline. We are moving from 2D pixels to 3D dots, LiDAR.
Light detection and ranging, yeah.
The transcript from Lutra Consulting focuses entirely on this. For those who don't know, can you explain what LiDAR actually is?
Sure. Imagine you're flying a plane or a drone over a forest. The device shoots a laser pulse at the ground, thousands and thousands of times per second. It just measures how long it takes for that pulse of light to bounce back to the sensor.
Okay.
If the pulse hits the top of a tree, it bounces back really fast. If it makes it all the way to the ground, it takes a little bit longer.
So you don't get a picture, you get a cloud of dots.
You get a point cloud, billions and billions of dots, each with a precise X, Y, and Z coordinate.
And the problem, historically, has been the size of these files, right? They're massive, terabytes.
Oh, absolutely. If you tried to load a raw.las file, which is the standard format, into older GIS software, your computer would just catch fire. You would run out of RAM trying to draw every single one of those billion dots at once.
But QGIS 3.32 brought in native processing for this, and specifically this thing called the COPC format. COPC, Cloud Optimized Point Cloud.
This is the game changer. Think of it like Netflix.
Okay.
When you watch a 4K movie on Netflix, you are not downloading the entire 50-gigabyte file before you press play, right?
Oh, it streams.
It streams. The server sends you just the bits of data you need for the second of video you are currently watching.
I see where this is going.
COPC does that for 3D maps. It organizes the points into a special tree structure, on-tree. When you're zoomed way out looking at the whole city, QGIS only asks the server for, say, 1% of the points, just enough to give you the general shape.
So it might look a little fuzzy, but it loads almost instantly.
Exactly. Then, as you zoom in on a specific house, QGIS automatically requests more detail for just that area. You can smoothly interact with a terabyte dataset on a normal laptop with 8 gigs of RAM because you are never holding the whole thing at once.
And it can stream this over the internet. The file doesn't even have to be on my computer.
That's the cloud optimized part. It can be on an Amazon S3 bucket or some other public data server. You just paste the URL into QGIS and it streams in like it was a local file.
That is wild. But just looking at a billion dots, I imagine it can be hard to interpret. It must just look like a fuzzy blob. This source mentions something called IDOM lighting.
Yeah, which sounds like a special effect from a sci-fi movie.
It does.
And it basically is. It's a visualization technique. Without it, a point cloud is just flat color. You can't really tell which dot is in front of which other dot. There's no depth perception.
Okay.
IDOM lighting uses the depth buffer, which is the distance of each point from the camera, to draw a subtle shadow around the edges of objects.
So the trees suddenly pop out from the ground?
Suddenly, you can see the texture of the leaves. You can see the sharp edge of a building's roof. It turns a mess of data into a recognizable 3D world, just with one checkbox.
And we can't talk about LiDAR in QGIS without mentioning the Poodle?
PDL, the Point Data Abstraction Library.
Right.
But yeah, the developers affectionately call it Poodle.
And QGIS wraps this library into its processing toolbox. So what can we actually do with the point cloud besides just looking at it?
The big one is ground classification.
What's that?
Imagine you want to know what the actual terrain looks like under a really dense forest. Maybe you're an archaeologist looking for ancient ruins.
Right.
The laser pulses from the plane can penetrate the canopy. Some pulses hit the leaves, but some make it all the way to the ground.
Okay.
PDL can run an algorithm. One is called the cloth simulation filter, which basically acts like dropping a virtual cloth over the point cloud. The cloth sits on top of the ground points, but it sort of falls through the gaps where the tree points are. It finds the lowest points.
So it can separate the ground from the non-ground.
It classifies every single point as either ground or not ground. And then you can just turn off the not ground points. You can digitally strip away the trees and reveal the bare earth model underneath.
That's how they found those massive Mayan cities in Guatemala recently, isn't it?
That is exactly how they did it. They used LiDAR to digitally deforest the jungle. And you can do that in QGIS now.
For free.
For free,
Huh.
on your laptop.
That is just, it's mind-blowing. But all of this point-and-click stuff, eventually you hit a wall, right? You need to do something 500 times. You need automation. This brings us to the engine room section, PyQGIS.
The power user's domain, yes.
The source material, the PyQGIS cookbook, makes it very clear. QGIS is built on Python.
It exposes its internal organs, its API, to Python. There is a Python console built right into the menu. You can just open it up and start typing commands.
Okay, give me a practical example. Why would a normal person ever touch this?
Laziness. Pure laziness is the mother of all scripting. Let's say you have 50 layers in your project, one for each state in the US, and you decide you want to change the transparency of all of them to 50%.
I would double-click the first one, go to the Style tab, change the opacity slider, click OK. Double-click the second one.
And 20 minutes later, you have carpal tunnel syndrome, and you hate your life.
Right.
With the Python console, you can write a simple for loop. It's maybe 3 lines of code. It says, for layer in all the layers, set the opacity to 0.5. You hit enter.
And they all just change instantly.
Instantly. All 50 of them. You can automate exports. You can write a script that says, for every layer in this group, zoom to its extent, export a PDF, name the PDF after the layer, and save it in this folder. You press enter and go get coffee. When you come back, all your work is done.
The cookbook seems really structured for non-programmers, too.
That's why it's called a cookbook. It's not a textbook. It's a book of recipes. It says, do you want to manipulate the table of contents? Copy and paste this code. Do you want to select features by an attribute? Copy and paste this code. You don't need to be a computer scientist. You just need to be what they call a script kiddie who knows how to copy-paste intelligently.
But even with Python, things go wrong. Let's get into our troubleshooting section based on the Common Errors Guide. Let's do a quick triage of the most annoying problems.
Let's do it.
Okay, problem number 1, the north arrow. I make a beautiful map layout. I put a north arrow on it. Then I decide to rotate my map a little to fit the page better. But the north arrow just keeps pointing straight up. It's wrong, and it looks ridiculous.
This is a classic. In the layout view, the north arrow is just a dumb image. It's an SVG graphic. It doesn't know it's connected to the map unless you explicitly introduce them to each other.
How do you do that?
In the Item Properties panel for the arrow, there's a setting for image rotation. And right under that is a checkbox that says Sync with Map. You have to check that, and you have to select which map frame on your page it should listen to. Once you link them, if you rotate the map, the arrow will spin right along with it.
Okay. Problem 2, invalid geometries. The guide mentions things like slipped polygons or self-intersections.
This usually happens when data is digitized carelessly or imported from a messy source. Imagine drawing a polygon shaped like a figure 8. The lines cross over each other. That's a self-intersection. In the real world, a piece of land cannot intersect itself. It's physically impossible.
But the computer allows you to draw it that way.
It lets you draw it, but the mathematical algorithms break when you try to calculate the area or do an analysis. QGIS will often throw an error and just stop processing.
So what's the fix?
There's a tool in the processing toolbox called, very creatively, Fix Geometries.
I like a tool that does what it says on the tin.
Exactly. You run your broken layer through that tool, and it analyzes every shape. It untangles the bow tie, it splits it into 2 valid polygons if necessary, and it saves a new, clean version of your data. It's like a spell checker for shapes.
Okay, last big one. Problem 3, file management. The Steve problem, as I'm calling it.
Ah, yes. Absolute paths. The killer of collaboration.
The guide warns strictly against saving projects with absolute paths. Why is that so bad?
An absolute path is the full, complete address of a file on your computer. See users Steve desktop my awesome project data rivers.shp.
Right.
If you save your project like that and then you email that project file to me, my computer looks for a user named Steve. I don't have a user named Steve. So the project opens up and it's just a long list of broken layers with red exclamation marks next to them.
Because it can't find the data.
It can't find the data, so you have to use relative paths.
And what does that mean?
It just means the project file says, the rivers file is in the data folder right next to me. It doesn't care whose computer it is or if the user's named Steve or Jane. As long as the project file and the data folder are kept together, it will always work.
So the rule is, create a single project folder for every.
You must be disciplined. Create one main folder. Put your .qgz project file in there. Put a subfolder called data in there. Keep them together. If you move the project, move the whole folder. And for the love of God, never ever work directly out of your downloads folder.
That is the path to madness. And one last little warning from the guide, the scratch layer. The little icon that looks like a memory chip.
The temporary layer, yes. This is important. When you run a tool, like our fixed geometries, tool QGIS doesn't automatically save the result to your hard drive. It creates a temporary layer in your computer's RAM to save time.
And it puts that little chip icon next to it in the layer list.
Right, to warn you. Because if QGIS crashes,
it's gone.
It's gone. If you close the project without saving it,
it's gone.
It's gone forever. It'll warn you. It'll say, discard temporary layers. And if you click yes without thinking, you just lost all your work.
So the rule is, if the result of a tool is good and you want to keep it, you have to right-click on it and choose Make Permanent.
Or Export Save Features As. Save it to a real file in your project's data folder immediately. Treat scratch layers as drafts, never as final products.
Good advice. As we wrap up here, let's look at the future a bit. The roadmap in the source material mentions version 4.0 is planned for February 2026.
That's the target, yeah. And it's going to be a pretty big shift because they're moving the whole application to Qt6.
The underlying graphics engine.
Right. It's a necessary move to make sure QGIS stays compatible with, Windows 12 or Mac OS, whatever comes next. But just like the shifts from version 2 to 3, it will likely break a lot of the third-party plugins. There will be some growing pains.
But that's the nature of this beast, isn't it? It's community-driven.
And that is the most important takeaway from all of this. QGIS isn't a product, it's a project. It's built by volunteers. The documentation we've been reading, written by volunteers. The translation of the interface into Spanish or Japanese. All done by volunteers.
The sources really encourage users to contribute, and they make it clear you don't need to be a coder to do that.
Not at all. If you find a bug, if you crash the software, reporting that bug with a clear step-by-step description is a huge contribution. Writing a little tutorial for a tool you figured out is a contribution. It's a true ecosystem.
It really is democratizing the way we see our world. And that leaves me with a final thought for you, the listener. We talked about QGIS 2 Web. We talked about streaming cloud-optimized point clouds from the internet. We are moving to a world where making a map is kind of an outdated concept. We're building digital twins.
Live, streaming, 3D models of reality.
And the barrier to entry is basically zero. The software is free. A huge amount of the data Landsat satellite imagery, Sentinel, USGS LiDAR, is mostly free and publicly available.
Anyone with a laptop and an internet connection can do it.
So what does that mean for privacy? What does it mean when anyone, not just the government, not just a big tech company, but your neighbor or a hobbyist down the street, can pull a LiDAR point cloud of your backyard, classify the vegetation, measure the height of your new fence to the centimeter, and publish it to an interactive web map in 15 minutes?
It means we are all living in a glass house now. The God's eye view isn't just for the CIA anymore. It's for everyone. And I don't think we as a society have really figured out the etiquette for that yet.
Something to chew on. Go download the LTR, grab some earthquake data, and start mapping. Just remember, latitude is Y.
And longitude is X.
We'll see you next time.